Good day. I am Irami A. Tibay, and with me are Ms. Dane Mariel Dawat and Mr. Max Lawrence Viado to present to you our paper entitled Vapor-Liquid Equilibrium Modeling of Methanol plus Ethyl Formate Binary Mixture. Allow me to present to you the abstract of the study. This study presents a rigorous and thermodynamically consistent vapor-liquid equilibria or VLE analysis for the highly non-ideal methanol plus ethyl formate binary system, a mixture that poses a significant challenge due to the formation of a minimum boiling azeotrope. The core objective was to address a technical gap in the existing literature by developing a comprehensively validated and integrated modeling package for the VLE dataset. Experimental data at 101.3 kilopascal confirmed the extreme non-ideality, with the azeotrope existing at approximately 0.61 x sub 1 and a temperature of 328 Kelvin. The consistently positive and asymmetrical excess Gibbs free energy provided conclusive evidence of non-ideal mixing necessitating the use of an advanced model. The group's methodology involved validating the binary interaction parameters of the non-random two-liquid model and subsequently integrating it with the Peng-Robinson equation of state using the modern gamma-phi approach. The final PR-Uniquac framework, which replaced NRTL model due to superior performance, was rigorously validated against the experimental VLE data, exhibiting superior predictive performance. It achieved the lowest average absolute deviation in both temperature at delta T 0.211 Kelvin and vapor phase composition of delta Y sub 1 0.007. Ultimately, the resulting Uniquac framework and its parameters enable accurate predictive simulation, validating pressure swing distillation as an energy-efficient method to overcome the azeotropic limitation.
For the introduction, I will be discussing the statement of the problem, research gap, and contribution of the study. Statement of the problem. The methanol plus ethyl formate system exhibits an azeotrope due to extreme non-ideality, preventing conventional distillation and requiring costly non-conventional separation. Research gap. Current VLE literature fails to provide a thermodynamically consistent gamma phi approach by integrating the NRTL model with the Peng-Robinson equation of state for this system. Contribution of the study. This study delivers a validated comparative VLE model solution integrating the Peng-Robinson Wong-Sandler Uniquac framework to provide the essential highest fidelity parameters required for the design and optimization of the pressure swing distillation sequence.
Moving on to the methodology. Our project addresses the difficult task of accurately predicting VLE behavior for the methanol plus ethyl formate solution, a model system for extreme non-ideality. The strong contrast in molecular association between the highly self-associating methanol and the polar ester causes a large positive deviation from ideality. Practically, this results in a minimum boiling azeotrope, which poses a significant hurdle to industrial separation. Crucially, we recognize the limitations of singular thermodynamic models. Neither the PREOS alone, which misses liquid phase association, nor activity coefficient models like Uniquac or NRTL alone, which lack the necessary volumetric and pressure corrections, are sufficient to model this system rigorously. To overcome these limitations, we structured our work around three core objectives. First, to ensure the highest level of thermodynamic accuracy, our objective was to model the mixture using a thermodynamically consistent, integrated framework such as the PR Wong-Sandler Uniquac model. Second, we focused on the crucial correlative step, utilizing experimental data to determine the optimized binary interaction parameters A12 and A21 that minimize the deviation between our model and the experimental reality. And finally, our goal was to leverage this validated model to predict and model the entire VLE phase behavior, the full PXY and TXY diagrams, as well as the excess properties of the system, providing the necessary data for industrial design validation. Our modeling approach employs a hierarchical model structure. We begin with Rail's law to establish the essential ideal baseline. This is the null hypothesis against which we measure all non-ideal behavior. Next, the Peng-Robinson equation of state is our primary tool for handling the physical non-ideality. The Peng-Robinson equation of state accounts for the non-ideal vapor phase and calculates all volume and pressure-dependent properties. To address the chemical non-ideality, we employed two liquid activity coefficient models. UNIQUAC was used for a correlative analysis because of its flexibility, and the two adjustable parameters allow for the highest accuracy fit to the experimental data, effectively modeling the strong energetic asymmetry due to methanol's hydrogen bonding. For predictive analysis, we used UNIFAC. This group contribution method allowed us to forecast the entire thermodynamic landscape, including excess properties, without relying on experimental binary data. The most important piece is the Wong-Sandler mixing rule. This rule acts as a bridge, linking the excess Gibbs free energy from UNIQUAC or UNIFAC directly into the Peng-Robinson equation of state. This integration forces the entire model to be thermodynamically consistent, allowing us to perform the rigorous 5-5 flash calculations necessary for accurate VLE prediction. Our computational methodology was structured in three distinct phases to ensure a complete and rigorous thermodynamic analysis of the system. The first is the baseline modeling. We started by establishing the fundamental data. This included pure component analysis using the Peng-Robinson equation of state to understand the non-ideal behavior of methanol and ethyl formate individually. We then built the ideal VLE phase diagrams using Rail's law as our essential baseline for comparison. Next is the predictive analysis. The core of our predictive work utilized integrated thermodynamic models, specifically the PRWS UNIFAC framework. This allowed us to forecast the system's behavior, including the excess properties and the non-ideal VLE phase diagram predictions, demonstrating the model's ability to anticipate the complex azeotropic behavior. Lastly is the correlative analysis. The final phase focused on validating the models against experimental data. This involved data reduction, where we converted raw VLE measurements into experimental excess Gibbs energy values. Finally, we performed parameter optimization, fitting the UNIQUAC model parameters to achieve the highest possible accuracy against the experimental data.
Results and discussion. For Section 1, Fundamental Data and Property Validation. Critical constants and endpoint parameters were validated for the use of Peng-Robinson equation of state inputs, ensuring the accuracy of residual property calculations. 3.2 Thermodynamic consistency testing. Gibbs-Duhem integral and direct test confirmed data consistency, which was supplemented by a residual plot validating UNIQUAC's excellent fit for excess Gibbs energy. 3.3 Verification of experimental methodology. The VLE apparatus integrity was validated by successfully measuring and confirming the known azeotrope of the ethyl acetate plus ethanol verification system. 3.4 Ideal VLE phase diagrams and excess properties. Analysis confirmed the definitive minimum boiling azeotrope at X1 is approximately 0.61 and the high positive excess Gibbs energy, which mandates the use of an activity coefficient model. 3.4.1, the isobaric curve showed low relative volatility near the azeotrope, preventing simple distillation. 3.4.2, a distinct pressure maximum confirmed the azeotrope and strong positive deviation from Raoult's law. 3.4.3, the positive excess Gibbs energy curve directly quantifies non-ideal mixing and justifies the excess Gibbs energy model. 3.5 Justification for correlative framework. The gamma phi framework was selected, pairing the liquid phase uniquark model to handle methanol's association with the Peng-Robinson equation of state for vapor phase fugacity. 3.6 Liquid and vapor phase activity coefficients. Liquid activity coefficients gamma 1 is greater than 1, confirming strong positive deviation and endothermic mixing with the asymmetry validating the need for the uniquark model. 3.7 Pure component fugacity coefficients at varying conditions. The consistent deviation of pure component fugacity coefficients from unity confirms the highly non-ideal vapor phase and mandates the use of the Peng-Robinson equation of state. 3.8 Mixture fugacity coefficients at varying conditions. Mixture fugacity coefficients confirm that while the vapor phase is largely ideal at VLE pressure, the gamma phi approach is necessary for maximum thermodynamic consistency. 3.9 Uniquark parameter regression and molar interpretation. Nonlinear regression determined the positive and asymmetrical uniquark parameters, quantitatively confirming the liquid phase repulsive interactions. 3.10 Final model validation and quantitative performance. The Peng-Robinson uniquark model achieved superior predictive capability confirmed by the lowest average absolute deviation in temperature and vapor composition. Lastly, 3.11 Thermodynamic basis for advanced separation and process design. The high excess Gibbs energy and pressure dependent VLE shift confirm the feasibility of pressure swing distillation with the validated parameters for process design.
In conclusion, the study delivered In conclusion, the study delivered a rigorous and thermodynamically consistent vapor-liquid equilibria, or VLE analysis for the highly non-ideal methanol and ethyl formate binary system. The group first confirmed the experimental VLE data's thermodynamic soundness using the Gibbs-Duhem integral and direct tests. The system's significant positive deviation from Rolle's law and the asymmetrical excess Gibbs free energy profile fully justified the need for an advanced activity coefficient approach. Crucially, the group employed the gamma phi approach, utilizing the Peng-Robinson equation of state for the vapor phase and the Uniquark model for the liquid phase, selected for its ability to account for the structural complexity of the components. The binary interaction parameters for the Uniquark model were determined with high precision using particle swarm optimization, resulting in the final PR Uniquark framework. This framework exhibited the highest fidelity to the experimental data, achieving the lowest average absolute deviation in temperature at just 0.211 Kelvin and in vapor phase composition at delta Y sub 1, 0.007. Finally, leveraging the rigorous thermodynamic foundation and supported by the analysis of the VLE boundary shift with pressure, the group quantitatively validated pressure swing distillation as the most energy efficient non-conventional separation technique for overcoming the minimum boiling azeotropic limitation. These accurately correlated PR Uniquark parameters are now the foundational input required to simulate and optimize advanced separation columns for the industrial purification of mixtures containing methanol and ethyl formate.